This video is for solving exponential equations using exponent properties. These types of problems are the type that as a student would make me pause and make my stomach uncomfortable because they looked complicated and impossible to understand. And hopefully in this video we will demystify that process and you will see that even someone like me can solve these problems. So when you go to the class webs page, you're going to have two videos, only one video from Khan going over it as well as our video. And then you're going to have the questions. The last thing I put here was this test review, and the reason is next week we're actually going to have the unit test coming up. So I do want you, 2 weeks from yesterday will be the unit test. So you may want to take some time to review earlier topics. Again, if you're getting this kind of stuff, you're probably getting most of the previous topics, but it is always worth looking at them just so you're familiar with what types of questions they'll ask, so nothing kind of surprises you when you decide to take the test. You can email me if you have any questions directly, and that can be a good way to do it. Also, on Friday, we're going to be having an optional video chat for the class. You are welcome to pop in if you have any questions. You can ask those. Otherwise, I'll just go over some examples. Now, it might be the type of thing where, one or two people show up. It might be the type of thing where a lot of people are having questions, and that's fine too. So this link should take you to a video chat, which should work Zoom. I'm still a little bit new to using Zoom, so hopefully there's no technical difficulties, but this is just a link to the Zoom meeting I set up. And it doesn't have a password, so you shouldn't need one to get in. It is low security. If anyone wants to steal the secrets about how to use exponent rules, they are welcome to do that. Yeah, that's about it. So let's actually look at these problems. So the first problem is a blessing. So whenever you get one of these styles where it says equals 1, there's a couple of them, and you might get one like this. These are the best you can possibly get. Because you can actually exploit a fact when you get one of these types of problems. So if it says equals 1 here, there's a very specific way to solve this problem. And so I thought we would go over this one first because it's the one that has a nice clear answer with how to deal with it. So when this happens, what you have to say is you have to know that any number raised to the 0 power equals 1. So if I have 17 to the 0 power, that equals 1. If I have 256 to the 0th power, that equals 1. If I have negative blah, blah, blah raised to the 0th power, that's going to give me 1, right? If I put 0 to the 0th power, that's going to give me 1 by most people's definitions. So the beautiful thing about this is we immediately don't have to worry about this annoying fraction thing. It is dead to us because all we care about is this thing. We know that this must be to the 0th power. So we know that 0 is equal to 5x minus 4 because something to the 0th power would give us 1, and that's the only way we could really get 1. Unless, of course, our fraction was 1, but then that wouldn't be an issue. So when you get these types of problems, just keep in mind that your exponent value here is going to have to equal to 0. Once we know our exponent is equal to 0, it's not too bad to solve this. We get 5x minus 4 equals 0. If I want to solve this, I need to isolate x, so I need to get rid of this other term first, and then I'll deal with the coefficient later. So we're going to get rid of the other term by adding 4 to both sides. I get 5x equals 0 plus 4 is 4. And then I want to divide by the coefficient 5 to get rid of that. So I have to do it to both sides to be fair to my equation. And I get x equals 4 over 5 to make this equation true. And that is my answer. So if you get this type of equation, remember this thing equals 0 because any number to the 0th power equals 1. So these types are actually kind of nice, but you do kind of have to know what you're doing because they're a little bit weird in that way. All right, so we're going to delete that and try another one. So if you get one thing from this video, that first problem is kind of nice. All right, so now is where things get a little bit hairier. So we need to solve the exponential equation for x, and it's not immediately clear how I should do this. I've got a 3 as a base here and 81 as a base here, so a lot of my exponent rules don't apply, because my exponent rules basically happen when one of two things is true. Either I have the same base, or I have the same exponent. I definitely don't have the same exponent, and I don't have the same base either. So what I need to do in this case is I need to force my equation to have the same base. And in all of these problems, if there's a way to solve them, which there is, there will be some way to get the bases the same. And you'll notice 3 and 81 have an interesting relationship. 3 is actually a root of 81. So if I have 81, I could break this down into 9 and 9, and I could break each of my 9s down into 3 and 3. And what we'll notice is 3 times 3 times 3 times 3, this bottom thing, that is equal to 81. I could also say 3 to the 4th power is equal to 81. And the reason that this is useful is I can rewrite this equation slightly now. I can rewrite this as 3 to the 4x plus 5 equals 3 to the 4, and I'm replacing 81. This 81 I'm replacing with this 3 to the 4 right here. And then I still have to use my same exponent, negative 3/4. So we're going to say to the negative 3/4. And so this is what the trick to getting all these problems into a doable form is. You have to figure out a way to get the same bases. And so 3 and 81 have relationship. You might see like a 3 and a 27. You might see like a 4 and a 64. You might see a 5 and a 125. You might see a 7 and a 49. You might see an 8 and a 64. Those types of things. And the reality is, it's kind of hard to see these, but there's actually only so many combinations. And if you're really not sure, just kind of look at these numbers and try dividing them by common numbers that we often see. So numbers between like 0 and 12. There'll probably be some sort of root that you can use. Okay, so let's delete all of that. And let's continue on with our problem. So we found that this was a base of 3, and we could rewrite this as 3 to the 4th raised to the negative 3/4. Now, before I try to solve anything more, I'm actually going to simplify this a little bit more. I want to make this just 3, not 3 to the 4th. So what I'm going to do is I'm going to leave this side alone again. So we're just going to say 3 to the 4x plus 5. And in this side, I'm going to remember my exponent rule. And I have an exponent raised to another exponent. When I have an exponent raised to another exponent, so this would be this would be called the power rule. So a to the x to the y is a to the xy. So I can multiply these two exponents together. And so if I multiply these two exponents together, I have 4 times negative 3/4. And so this is going to be equal to 3 to the 4th times negative 3/4. When I do this, I'm actually going to have 4 times negative 3/4. Well, 4 times negative 3/4 will give me negative 3. And I could check that on my calculator. It gives me a nice whole number. But you kind of want to avoid your calculator because it might give you a decimal, which isn't very helpful. The other way to think about this is you have 4 multiplied by something, and then that thing is later divided by 4. So you're multiplying and dividing by 4. Those just cancel out. So we end up with, this is going to be 3 to the negative 3, because these 4's cancel out. Or another way of saying 4 times negative 3/4 is negative 3. So I end up with 3 to the 4x plus 5 equals 3 to the negative 3. Now, once I get here, this is where the problem gets nice and familiar. So if I have this raised to this exponent equals the exact same 3 raised to this exponent, what I know is this. I know that this thing must be the same as this thing, right? 4x plus 5 must be the same as negative 3, because these two statements are equivalent to each other. So I'm actually going to drop my bases now that I have everything exactly the same, and I'm going to say 4x plus 5 must be equal to negative 3. From here, what I can do is solve for x. So in order to solve for x, I'm going to get rid of this 5 by doing minus 5 to both sides, and I get 4x equals negative 8. And then I want to solve for x, and I want to solve for x. I'm trying to use the preposition for instead of the number for, but it sounds weird because we have a coefficient of 4. In any case, I'm going to divide by 4, and 4x divided by 4 is going to give us x. Negative 8 divided by 4 is going to give us negative 2. So we end up with a value of x equals exactly negative 2, and that is the answer for this one. So just pausing for a moment, thinking about how we approach these problems generally, is you're going to have two bases that are not the same. You need to figure out a way to get those bases to be the same. So look for a way to get same bases. And then after there, you're going to have to use some sort of exponent rule. Maybe you'll have to remember exponents to exponents. Maybe you'll have to remember something else. But it'll be something from this list probably. And once you do that, you can simplify until you get to a point where you get a nice equation like this. The last kind of tricky thing is we ended up here, 3 to the 4x plus 5 equals 3 to the negative 3. If you have the same bases equaling each other to the same exponents, then you know those exponents must be equal to each other. Once we knew that, we just did old-fashioned algebra, and we got x equals negative 2. Okay, so let's try another one. All right, so I've got a 4 and a 64. So how are these related to each other? So I need to get the same bases, and it's really 4 1 over 64. But I don't want to think about this as 1 over 64. I don't want to deal with fractions. So we're actually going to rewrite this as 4 to the 9 minus 6x, that won't change, equals, and I'm going to write this as 64 to the negative 1 power to the 10 over 3. And you'll see why in a moment. But if I want to get 64 to 4, well, 64 is related to 4. So 4 to the third power is 64. And you can kind of mess around with this, but that's kind of one of those relationships you'll eventually start almost memorizing. So we can rewrite this as, and let me erase this. So if I confuse you with that 64 to the negative 1, I think this might be a better way to think about it. So we could call this 1 over 4 to the third power, all of this raised to the 10 thirds. And the reason is I wanted to somehow get that same base. Now that I've got this same base, I need to remember my exponent rule, 4, 9 minus 6x. This is actually 1 over 4 to the third. It's not quite the same power. To get it to be the same power, it has to be a base of 4, not 1 over 4. And it's actually a really easy fix to do this. So you'll get a couple of these problems where it'll be like 1 over 25 and there'll be a 5 here. All you have to remember is 1 over 4 to the third is 4 to the negative 3. And I think that's on our exponent rules. Yes, a to the negative x is 1 over a to the x. So 1 over 4 to the third is the same as 4 to the negative 3. And so we end up with 4 to the 9 minus 6x is 4 to the negative 3. And that's, we'll put that in parentheses, raised to the 10 thirds. I have an exponent to an exponent. Our power rule states that we can multiply those. So I get 4 to the 9 minus 6x equals 4 to the negative 3 multiplied by 10 thirds. When I do negative 3 times 10 thirds, this will actually be a nice whole number. Negative 3 times 10 over 3. That's going to give us negative 10. Another way of thinking about this is our 3's cancel out. We have this negative sign left over that sticks with a 10. And so this becomes 4 to the 9 minus 6x equals 4 to the negative 10. Now this is really great because we've got the exact same bases, nothing too complicated going on. Now I can say that this exponent must be equal to this exponent because this raised to this is equal to this raised to this. So 4 raised to something equals 4 raised to something. Those two somethings must be equal to each other. So we will say 9 minus 6x equals negative 10. From here, it's a pretty straightforward algebra problem. So we're going to get rid of this other term, this 9 here. So we're going to subtract 9 from both sides. And I get negative 6x equals negative 10 minus 9 will give me negative 19. And then we are going to say that we will be dividing by negative 6 for both sides. And I end up getting x equals 19 over 6. It's really negative 19 over negative 6, but the negatives cancel out when you have negative on top and bottom. So our final answer is x is 19 over 6. And that is the answer for that one. So the key really is getting these to this point here. Figuring out a way to use our exponent rules in a clever way to make this 1 over 64 really 4 to the negative 3. Okay, let's look at another example. Okay, that was our previous example. Here we go. All right, so maybe pause and give yourself a second to think. How is our base 2 related to our base 1/8? Think if you can think of a way to make 1/8 look like 2. I'll give you just a second. All right, so pause the video if you want a second more to think, but maybe you realize that 8 is really 2 to the third. So this is really like 1 over 2 to the third. And I could express this as 2 to the 6x plus 7 equals 1 over 2 to the third. It's starting to look more familiar. And this thing raised to the 1 minus 5x. And this is awesome, except we want just a 2 in our numerator, not our denominator. So we're going to mess with this one to make it in the numerator. So 2 to the 6x plus 7 does not change. But for this over here, we're going to actually say this is 2 to the negative 3. And we can do that because of our exponent rule, which says 1 over any base to a fraction is that same base to the negative value of that exponent. So we end up with that, and then we cannot forget our other exponents, which is 1 minus 5x, and we can go from here. So I'm going to keep this again, 2 to the 6x plus 7 equals, and now I can do some stuff here. I can distribute this negative 3 to my 1 and my negative 5x. And the reason is I'm multiplying. So I'm going to do negative 3 times 1 will give me 2 to the negative 3. And then I'm going to do negative 3 times negative 5x. That'll give me plus 15x. And in this case, I end up saying that 6x plus 7 is equivalent to negative 3 plus 15x. So we're going to say 6x plus 7 equals negative 3 plus 15x. And now we have to solve an algebra problem where I have my variable on both sides. It may have been a while since we did this last, so just to remember, if you have this type of situation where your variable is on both sides, like it is on this side and this side, what you want to do is somehow get your variable to one side, and then it will be a normal algebra problem. So in this case, I'm going to subtract 6x from both sides. You could subtract 15x from both sides as well, but let's do it this way. So 6x minus 6x, those cancel out. So this side will not have x's on it, good, equals negative 3. And then 15x minus 6x will give me 9x. So we're going to say negative 3 plus 9x. From here, it is a very normal algebra problem. So we're going to add 3 to both sides. And we get 10 equals 0 plus 9x. And so then we finally get x must be equal to 10 divided by 9, because I'm going to divide by 9 on both sides. So x equals 10 over 9 in this case. Okay, so these are long, challenging problems, as you guys can see. I'm going to wrap up this video here because it's getting a little bit longer, but remember, we can review these in our class chat on Friday at 2 p.m. If there are any issues with the time, so like if you have a conflict with another class, please send me a message and I'll reschedule it for some other time. That's totally fine. But otherwise, I will see you Friday at 2 p.m. With any questions you guys have. I left this chart next to the homework. Just keep it handy. It can be helpful if you're not sure what to do with the exponents sometimes. Okay, that is all.